All right, I'm going to turn it over to Parker and he'll get us going on this first lab then.
Sorry, just had to find my Zoom controls. They disappeared for a minute there. Fun stuff. So the first lab we have for you guys today is called containers. And that kind of ties in with the first concept of taking our monolith application that Casey introduced in the introduction and figuring out how we can package it into a container and run it locally using the Kubernetes cluster that you set up inside of your Cloud9 environment. So the goal is to set up our monolith application in our C9 environment. We're going to try and package the application, its configuration, and its dependencies all in one container, one single artifact to deploy. And then kind of the goal for you to learn from this lab is to have everybody understand a bit more about Docker, about containers, about Kubernetes, and specifically how we're packaging this application into a Kubernetes deployment. So as you can see, these kind of graphs here, we kind of went over the reference architecture for what the recommended way of deploying the Spring Trader application was, and what we're going to turn it into using Helm and various Kubernetes APIs. So the first thing we're going to cover is Docker. I hope that everybody here has at least heard of Docker before, or maybe has a very minimal experience with using Docker. And really the first step to transforming our application to run on Kubernetes is to kind of get more familiar with Docker so we can build an image. What we're going to do is we're going to review some best practices for writing what's called a Docker file. In particular, we're going to focus on concepts of Docker image layers, multi-stage builds, base images, and processes. And I'm going to go into depth a little bit for each of these. So I don't have the same fancy setup that Casey does, where I see the participants, everybody in the Zoom call on another screen. So go ahead and drop a comment in the general Slack channel if you have any questions while I'm going over this, or feel free to just speak up. We can kind of go over that whenever you happen to have questions. But I'll try and pause during different parts of this and see if anybody has any questions of what I'm talking about. So let's talk about Docker layers. So a Docker image is built using a series of layers, and each of these layers is really just a delta between what has changed in a current layer in relation to a previous layer. So it really builds on top of each other. So these instructions in a Docker file need to be ordered in a very specific manner to take advantage of the ability for Docker to cache different layers in terms of storage and reducing your image size. So an example of this we kind of see right here. We have our order of instructions. So one thing that we don't want to do is order our instructions like this. So what we have a from Ubuntu, right? So our base image is just an Ubuntu image. We are copying over our source code into a folder called Spring Trader. And then we are running apt-get update and apt-get install to install the JDK for this to run on, okay? Does anybody have an idea for why you do not want to order your instructions this way? Feel free to just speak up. Nobody. Well, the reason why you don't want to do this is because this layer right here, this copying our source code to our Spring Trader folder, is the layer that is most likely to change between iterations of your application, right? The JDK, specifically JDK 8, does not change very frequently, believe it or not. So what we want to do is we want to run those instructions first. So we have our base layer, we have our apt-get update that builds on that base layer, right? It's a delta. Then we have our apt-get install that builds on our apt-get update. And then we have our copying our source code, right? So this layer in active development, your source code is the most likely thing to change rather than dependencies to run your application. So we want to copy that last. So these layers can be reused into a cache. It reduces the amount of time that it takes for our Docker image to be built, and it reduces the size because Docker images are stored using layers, so we don't have to recompute these layers every single time. Cool? So the next thing we're going to talk about are dependency layers, right? So even knowing that our source code is the most likely thing to change with development iterations of your application, even in that, there are still different parts of your source code that are more likely to change in relation to other parts of your source code, right? So let's talk about dependencies, for example, right? In a typical feature that a developer team is building, typically the actual source code of the application is more likely to be changed than some Gradle dependencies that you happen to be building into your application. You could apply this to other languages too, like Node.js has a package.json file that tracks all of the different dependencies you have for your app. That file is, while it does change from time to time, right? Maybe a new feature has to install a new dependency and that'll change. It's typically the least likely thing in your code base to change when working on a new feature, right? You don't add dependencies every time you construct a new feature, or at least I hope you don't. So what we're going to do is we're going to copy those things in first, right? So if you have a feature that does not change any of these files, we now get to reuse this Docker layer for the next time that we build our image, which kind of, again, reduces the amount of time it takes to build these images and reduces the amount of storage that this image takes up. So we're copying our build.gradle, our Gradle properties, our settings, and our Gradle wrapper. We're copying the wrapper folder, and then we're running Gradle build, right? So the idea here is copy everything we need to install dependencies, then install our dependencies, and then we can go down to our next step where we actually copy over our source code, right? So we already have our dependencies pre-baked into a layer that we can cache and reuse in subsequent builds. So the next thing we want to do is we want to be specific and again, order things in an order at which things are, the things that are less likely to change are at the top of your file, and the things that are most likely to change are at the bottom, right? So if you do something like copy ... and you copy everything in your working directory into the Docker container, that layer is probably going to change every single time you run your builds, right? Because one file in that glob of files is guaranteed to change. I would hope so, at least, if you're working on a new feature, right? So what we can do is we can order these copy directives in an order, again, from packages or folders that are least likely to change. These async services, this chaos service, this data service, all the way down to services that are most likely to change. Our web folder, which contains our, our controllers and whatnot, those typically change very frequently. So we'll put those in last, and we'll make sure that if a layer is going to be invalidated and cause a cache miss, it'll be this last one here. So these ones can be reused. Lastly, because our Docker images, again, are stored in layers, and layers are just a delta from one layer to the next, we want to make sure that we do appropriate cleanup when we're building our image, right? So as you can see here, this one run statement, this is all one single layer with a lot of different commands that are chained with double ampersand here, right? So we're going to grab our zip file that has Groovy in it. We're going to unzip it. We're going to move our Groovy binary to our local bin folder. We're going to move this one too, and then we're going to remove this zip file that we downloaded originally, right? So the point of this is, if we had all of these commands as separate run statements, it would actually result in the Docker image being larger, which is something that a lot of people don't realize, especially this last one here. It's kind of interesting to think about, but this last line here, if this was a separate run statement, even though it's cleaning up a zip file, it actually results in a larger image, right? Because there is still a previous layer that has that zip file in it, which allows this layer to remove that zip file. So it's actually going to be larger if you do these in separate steps. So we want to make sure that we clean up after ourselves, all within the context of that single layer. Does anybody have any questions about this before I move on to the next concept? Feel free to just speak up. All right, let's keep going. Multi-stage builds. So multi-stage build is a relatively newer feature of Docker. I think it's 2 or 3 years old, maybe less than that, I'm not sure. I started using it around 2 years ago. It's really a game changer for how you build small and secure Docker images. So one of the challenges that you have with, let's say, compiled languages like Java, for example, is to make sure that your resulting image is as small as it possibly can be, and 2, only has the bare minimum software installed in it required to run your application. So for those of you who are familiar with languages like Java, you'll know that there are 2 different tools that you use very frequently within the context of a, oh, sorry, somebody have a question? Nope, okay. There's 2 tools that you use very frequently within the context of writing Java applications. There's your JDK, your Java Development Kit, that you use to actually compile Java code into bytecode. And then you've got your JRE, your Java runtime environment, that actually runs the code, which represents your application, right? So On the let's say if we're talking about VMs, for example, one of the things that what we would do on a VM that's running a JVM application is we wouldn't actually have a need to install a JDK on it, right? You don't need that to run Java. You only need a Java runtime environment. Likewise, if you have a build server, you generally don't need the JRE on that. You would only really need the JDK because you really only need to compile your application into a WAR file or into a jar file and then ship it somewhere for it to be deployed. So we can use that same concept in containers here to understand how we can have separate build stages specifically for compiling your app versus the run stage, which will actually be your final image that gets deployed to a Kubernetes cluster. So right here, we've got from OpenJDK. So we're actually saying as builder here. So this lets Docker know this is going to be a multi-stage build and this stage is going to be reused. We're going to copy our source code into our Docker context. We're going to run Gradle clean build release. So that's actually going to build a WAR file for us or a jar file. And then we have another stage. We have a separate from. So from vfabric as runner. This is kind of just pseudocode here a little bit. There was in a Docker file that looks like this, a previous stage called vfabric. We're going to copy, we have our special syntax here, -- from equals builder. We're going to copy this WAR file that was built inside of the builder into our Spring Trader web app, Spring Trader WAR file location, right? So the point of this is now this vfabric stage doesn't have to have JDK on it. And that's important for two reasons, okay? The first reason is, again, it makes the image size smaller. If you don't need the JDK, it's a rather large dependency to have installed on a Docker container. You just don't include it, right? The second reason is for security. So if your running container has the JDK on it, has the ability to compile code, that means a malicious individual who happens to gain access to your container has the ability to write and compile code on that container. Right, so typically you want to make it as difficult as possible for somebody to be able to do that. So you wouldn't want to have the JDK or any other compiling tools like maybe C++, for example. You wouldn't want to have GCC installed in your resulting container. Does that make sense? Everybody understand that? Any questions?
Yes, I have a question. So when you have the final image built, right? That image, which going to be the last image that we're going to create several images out of this multi-stage?
Right. So that's a good question. Typically, it's the last from directive in your Docker file and then the subsequent lines below it. But one of the nice things about running Docker is you can actually target different stages if you want to, right? So what you can do during a Docker build is you can say, hey, I want to target this builder stage only. And then the resulting Docker image that it produces is only that builder stage. But typically you would have, in most cases, what I've seen is two separate stages, right? You've got your builder and you've got your runner. And if you just run a straight Docker build on that, the result is really going to be your runner. And the layers that end up getting uploaded when you do a Docker push are only the layers required for that runner. So maybe your runner just has like a, just like copying some source code and running Gradle, or just, if it was a Node.js app running Node index or server.js.
Perfect. Perfect. Thank you. Yeah. Totally.
Awesome.
Thanks.
Anybody else? Trying to keep an eye on general here too. Okay, looks like we're good to go here. So let's talk about base images. So base images are a way for you as a maintainer of your application's Docker image to make it easier for you to understand where your dependencies are coming from and not have to manage some of those things yourself. So here we have a don't. We do not want to just run a base image of some bare bones operating system like Ubuntu or CentOS and run yum install JDK ourselves, right? You can kind of see how this example could expand for other things that you might need during the process of building your application. Maybe Git, maybe curl. Maybe if you have like an application that's multilingual, you would have a bunch of different dependencies on that. What you would really want to do instead is find images like the OpenJDK image, for example, that already has an official maintainer and already does a pretty good job of packaging this base image with all the build tools that you should need to deploy or to build, in this case, a Java application. You'll find base images for pretty much every language you can think of. So these images are typically just one word here, so just OpenJDK. That's how you can tell it's an official Docker image. So you might see some for Node.js too. So like from Node.js:12 if you want a Node 12 image, or from Golang :1.13 if you want a Go image. But in general, you want to look for images that already have a maintainer and already have the dependencies that you need to build your app installed. The other thing we want to do is make sure that we use specific tags when we are pulling from these base images, right? So this is actually a pretty bad example for making sure that our application doesn't accidentally update itself without us knowing. So if you do from OpenJDK like this, oh, whoops, thank you, dictionary. If you do from OpenJDK like this, Docker is going to assume you want the latest one every time. Chances are you don't actually want the latest one. So if a new JDK version gets dropped overnight and you run a subsequent Docker build the next day, it's going to update your app for you. And typically that can result in a lot of fun, interesting debugging issues that you can trace down to right here, which is us not using a tag. So in this example, we want to make sure we're using from OpenJDK 7, so we're not accidentally updating to 8 or 9 or 10 or what have you. And of course, for tags like this, for 7, there's actually a lot more specific tags you can get into. You can pin minor versions, you can pin patch versions, you can customize typically the underlying operating system that's running here. There's a lot of options. If you go on Docker Hub and search for the OpenJDK images, there's a ton of tags that you can pick from to really narrow down to exactly what you're looking for. And then we are going to have a little lesson on using various stage images. So kind of what I was talking about before, when you use Docker build, you can actually target specific stages. So you can have various builder stages in one Docker file and various run stages in one Docker file. So you can use the exact same Docker file and produce 2 different images if you would like to. That's something that we'll be doing inside of Lab 1 for our Spring Trader application. So we've got our vFabric base stage here, a SQL Fire stage that essentially uses vFabric and then renames it to SQL Fire DB. And then we have another runner stage that also pulls from this vFabric stage. So we're reusing that same stage for 2 different purposes. Any questions on this?
Hi, yes, I have a question. Can you hear me?
Yep.
Okay, so it's not basically a technical question because I'm a little bit late. So I'm just interested in 2 things. Would I be able to see a recording of this webinar after it ends, so I can just fill the gaps from the beginning because I wasn't here at the beginning? And also, could I try this after with a video recording and video and to be provided with this URL that you're using for your lab, so I can try all these steps on my own afterward?
For sure. Yeah, so I would have you reach out to Matt. I don't know exactly how the recording is going to be distributed, but I know this is being recorded, and I think we'll email everybody or something afterwards. If you just want to go ahead and reach out to Matt about that. One thing that we always do after these labs is, you know, the idea of the lab is that you're working inside of a Kubernetes cluster that we are running in our AWS account that we're paying for. We typically keep that cluster up about a week after the lab, so you can revisit anytime you want, tomorrow, Friday, or even next week or over the weekend, and run through the labs on your own if you wanted to do that at your own pace. All you really need is access to the Slack account, and then yeah, that would pretty much be it. Does that answer your question?
Great. Thank you.
Awesome.
That's all I want. Thank you.
Perfect. Okay, so we're going to go to the next lesson for Docker here, and which is the idea of running processes in our container. So this one's kind of short. The recommendation that we have and most people have for Docker containers is to only run a single process in every container. And there's a good reason for that. Well, there's actually multiple reasons for it. The first is simplicity. So when you run multiple processes in one container, it kind of gives you a requirement that you have to handle your own scripting within the container to understand when the application might need to start in a specific order. So maybe if you're running 2 processes and one depends on the other, it's now up to you to make sure that one process starts and then listens for that, and then the other one starts after that. So that running 1 per container means that you're allowed to just run 2 containers, and then whatever orchestration platform you happen to be using can coordinate that for you. So in our case, Kubernetes will help us with that, as we'll see inside of Lab 1. So reliability, again, if you're using a container orchestrator like Kubernetes or Docker Compose, and your container has more than 1 process in it, typically your orchestration platform isn't going to understand that that means that your container needs to be restarted. So then the onus is then onto you, if you're running multiple processes in one container, to detect when one of those processes is killed and either gracefully restart it or send some kind of termination signal to the other one so that your orchestration engine knows how to restart it. So that just makes it a lot simpler if we just use one process per container. And then scalability, again, if we have two processes in one container, you're kind of coupling those together, which means that they can't independently scale. So your orchestration engine like Kubernetes can't allocate more resources to only one process and one process alone. It makes it very difficult for those to scale independently of each other. So in our entry point for our final Docker file, we typically like to use this form where we have some square brackets with some strings that represent how we're running. So we're running, in this case, a shell script. We're passing arguments of run and then Spring Trader. Typically, this form is preferred because this is the most common way to allow termination signals from your orchestrator, in this case, Kubernetes, to reach your actual single process that your container is running in. So if Kubernetes wants to kill a pod in order for it to be restarted, it'll send like a sigterm or a sigint to your container, and this exec form helps make sure that that termination signal reaches the process correctly. Any questions on that? Okay. All right, let's talk about Kubernetes. So Casey already kind of talked a lot about some of the fundamentals of Kubernetes and how we're going to be using it. I'm going to be going over Kubernetes with the context of how we're going to use it inside of Lab 1, as well as how we're going to use it with our Spring Trader application. So we're gonna focus on 4 main APIs in Kubernetes. So you've got our deployment. Casey kind of already talked about that. That's a nice way to make sure that our pods that run our application are managed for us, so we don't have to create pods directly. We're going to have a stateful set. So a stateful set is kind of a special type of deployment that allows you to also provision persistent volumes that can automatically be attached to any containers inside of your stateful set. We're going to be using that for our SQL Fire database. We've got a service. Again, Casey talked about this. Service is a way to allow other containers to other deployments within inside of Kubernetes to access some pods within your cluster. We're also going to have a job, which is a resource that runs a pod until completion. So our job is going to be responsible for seeding our Spring Trader application with both the database schema and the initial fake data that your application is going to be serving. So we kind of talked about this already. I'm not going to go over that too much here. So let's talk about deployments. So something that we didn't mention in the introduction here is how we're going to specifically use deployments to capture what we need to do with Spring Trader. So we're going to go over a few things here. We're going to go over resource requests and limits to make sure that our Spring Trader app has the necessary resources required to run and function correctly. We're going to go over liveliness and readiness probes to allow us as an operator of our application to tell Kubernetes when to detect that the application needs to be restarted, or when to detect that it is now okay for traffic to start hitting the Spring Trader app. And we're going to talk about init containers, which is something that we can use to help us control the life cycle of our deployment and make sure that all dependencies that our pods have are able to run before our pods are spun up, so that make sure that they're all in the correct order. So let's talk about resources. So when you create a pod, the Kubernetes scheduler uses resources that are defined within your Kubernetes manifest files to adequately select a node for which your pod can run on. So each node, so in our case, we're using EKS, right? So all of our nodes are EC2 instances that have a finite amount of resources. I think we're using XL nodes for the most part. So that's 4 vCPUs and 16 gigs of memory. And if we have 10 of those nodes, right, that's obviously a lot of resources, but it's still a finite amount of resources. We want to make sure that the scheduler knows that when it's trying to decide a place for your pod to run, it can kind of take into account, well, here's all my nodes, here's all the resources they have, here's all the containers that are running on them now. So the best place to schedule this is probably a node that already has plenty of resources available for my pod to run. So the way that we can help Kubernetes with this is by setting resource requests and limits. So you can kind of see the YAML that looks like for here for setting these resource requests and limits. And this diagram kind of helps explain what the differences between these are. So our CPU requests are essentially the bare minimum that your application needs in order to do its job correctly. These resources are guaranteed to the pod In this case, you will always have a bare minimum of 100 millicores, so about 10% of one vCPU allocated to your container. You will never have less than that. The other thing that we are setting here are limits. So what we've got our limit set to is 200 millicores. So again, that's going to be 20% of a vCPU. The limit control is kind of like a burst, right? So when you set a limit, that you're essentially telling Kubernetes, hey, if this container needs to go over 100 millicores, you can do that if it makes sense for the scheduler, but it's hard capped at 200 millicores. Okay, so you're kind of given some wiggle room if you happen to have some burst of activity where maybe you have kind of like a peak usage time during the day where your application is maybe getting more traffic than normal. Or in the case of JVM apps, a lot of times that we set limits is to make sure that when the JVM first starts, when running the container, it can kind of spike for a little bit to give it all the resources it needs to start up. And then it kind of settles down after a while and kind of fluctuates between 0 and the amount that you're requesting. So limits are just kind of there to provide a little bit of wiggle room, but they're not guaranteed to you, okay? So this is how we would represent this in YAML. So in resource requests, we have about a gig and a half of memory. We've got 256 millicores, which is about a fourth, give or take. And then for limits, we have 2 gigs of memory and 1 vCPU. So we can burst up to that if the scheduler will allow it, if there are resources on the node to allow it to burst. Any questions on this? I want to emphasize, this is a really important concept to make sure that we are defining these correctly, because this allows the scheduler to do its job correctly. If you don't define any resources or limits for your applications, there's nothing stopping the scheduler from just putting every pod on one node if it feels like, and that's generally not going to work very well for you. Let's talk about probes. So the other way that we can help Kubernetes decide when the appropriate time to restart your pods are, or to send traffic to your pods, is by using these liveliness and these readiness probes. So the readiness probe is what tells Kubernetes when your container can be marked as ready. When your container is marked as ready, it is now allowed to receive traffic from your services. So this pod's IP address will be added to the list of endpoints that make up a service as soon as it's marked as ready. The liveliness probe is a bit different. The liveliness probe indicates whether or not the container needs to be restarted, okay? So if the liveliness probe starts to fail, the kubelet knows it needs to kill this container, mark it as unready, and then kill it, and then restart it in order to get back into a stable state here. So when we define our readiness probes and liveliness probes for our Spring Chitter app, it kind of looks like this. So we're going to run an HTTP GET. We're going to make sure the path is /spring nanotrader web. That's where our app is being served from. We're going to send it to port 8080. We aren't going to start the readiness probe until 30 seconds after the Kubernetes, or until the container has started. Okay, so this kind of gives the JVM time to start up and get running. And after 30 seconds, we're going to start sending readiness probes to it to make sure that it's running. The liveliness probe is pretty much the same. There's nothing inherently wrong with making your liveliness probe the same as your readiness probe. But just kind of understand that there may be situations where you want to mark your pod as not ready, but don't want to restart it, and vice versa. That kind of depends on the business logic of your app and what it's trying to do. So the developers or the operators of those applications would know best when to decide a app is ready to be just forcibly killed and restarted, or just needs to be marked unready and then maybe serve like a 503 bad gateway to your client so it has time to catch up with whatever it was doing. Does that make sense to everybody? Does everybody understand the difference between these two? Take a swig of water while I wait. No questions. All right, let's talk about init containers. So like Casey mentioned earlier, pods can have multiple containers running apps within at the same time. And that also extends to containers that are used to seed your actual runtime containers, or run some kind of prep work to maybe fill an attached volume with some data, or maybe wait for another service to start before your service starts. You can use init containers to essentially run before the app actually starts. So what we're going to use the init containers for in this case is to make sure that our Spring Trader application does not attempt to start until both of these conditions are true, right? So what we're going to do is we're going to wait until our database server is running. We're running our database as a pod in our Kubernetes cluster. There's no point in starting our app if the database isn't running because the app's just going to fail, right? So we're going to use an init container to make sure that that database server has started before we attempt to start the Spring Trader app. So that's the first thing we're going to do. The second thing we're going to wait for, so again, this happens in order. So we're going to wait for this first, and then we're going to wait for a particular job that we create called generate schema, which generates a schema for your database. We're going to make sure that our init container waits for that job to be finished. Because again, we don't want to start the app and have it interact with a database that doesn't have a complete schema yet. Okay, so one of the things that we'll do when we start the app is actually seed the database with some fake data, some fake stock data, but we need the schema first before we can do that. So we're going to wait for that to be finished. Does that make sense to everybody? Does that make sense as a use case for why you'd want to use init containers?
Yep.
Awesome. Let's talk about stateful sets. So I kind of brushed up on stateful sets before. They're really useful as a unique resource, different than deployments, to allow you to automatically provision volumes that can be attached to your pods. So that way your pods can have persistent data. So when they restart, you don't lose everything. So that's a very important quality for things like a database, right? When your database restarts, you don't want to lose all the data inside of it. You want to make sure that data is available for you the next time that pod starts. So what we do here is we've got a persistent volume attached to our NanoDB server. Our NanoDB server is going to have a volume called SQLF data. We're going to do a read, write once access mode, which allows us to both read and write from this volume for this particular pod. Our storage class, typically your storage class kind of depends on what cloud provider you're running on. In this case, GP2 is the storage class we use for AWS. You'll have different storage classes for if you're running OpenShift on-prem, or if you're running in like Google Kubernetes Engine or Azure Kubernetes Service. And then we're saying when you create this persistent volume claim, we want to build a 2 GB persistent disk. So we want to have room for 2 GB worth of storage here. So the container here for our SQL Fire script is going to use a script to launch this database in the background. So the problem with that is that we don't really have a way to monitor that process if it's being launched in the background, right? So if that process exits, there's no way for Kubernetes to know whether or not that needs to be restarted. So we're actually going to tail the logs of this process, so that way when the process exits, our tail also exits, and thus the Kubernetes knows that it needs to restart that pod. So you can see we're running our discovery address here. We're binding to 127.0.0.1, and then we're tailing that log that it produces. So we're done tailing when the process exits. So you can see that there. We've got our probes here. So again, our probes are making sure that our pod is 1, able to receive traffic, and 2, doesn't need to be restarted. Those are our readiness and liveliness probes. The previous example of probes showed you how to use HTTP calls to query things, which makes sense if you have a web server or an API, but it doesn't really make sense for a database, right? So the other option that you have is you can actually execute a command on the container in order to check whether or not it needs to be restarted or whether it's ready to receive traffic. So we're going to run a shell, and we're going to essentially grep against the log and see the statement started and ready to accept connections. So if we see that log statement, now we know that this pod can be marked as ready, and we can start receiving traffic from our services. So maybe not the most graceful way of doing it, but sometimes when you're containerizing older applications like this, this is the best that you've got. So this is how we were able to solve that problem. And then again, we've got our init container here to make sure that our database has the volume with necessary directories created ahead of time. So we're just going to run our init container, and we're just going to make a couple of directories here. I guess this is only one directory. No, there's 2. So locator 1 and server 1. We're making these directories so that by the time the container actually starts, those directories will be there inside of that volume. So again, this is kind of showing the concept of how init containers and the runtime containers will both share these volumes that are being created by the stateful sets. You can provision it ahead of time with some directories and then start seeding it with initial data. Any questions on this? I am going a little fast here because I want to make sure that we have time for everything else and don't want to cut into people's lunch. All right, let's talk about services. There's not a whole lot to elaborate on here that wasn't already covered by Casey. So we are going to be creating a few services here. So we have our NanoDB server that we are creating. It's actually going to expose 2 ports, right? So if you start to send traffic to this service, you will have the option of using port 1527 or 1528, depending on what you're trying to do. We're also going to have a service specifically for SpringTrader to make sure that we can route traffic to its port that it's listening on with HTTP, which is 8080. One thing that we're doing is we're naming these ports. It's not necessarily required, but if you name your ports in your service and in your container or in your pod definition, you can reference those ports by name, which kind of makes it easier to understand where traffic's going, but it's not something that you have to do. So in this case, we're just using our service here is accepting traffic on port 8080, and then it's also sending traffic to all pods with this label to port 8080. So it's just listening and then sending traffic on the same port. Any questions on services? All right. Finally, we have our jobs. So we are going to be creating a couple of jobs here that allow us to provision our initial schema for our database, as well as start seeding it with some fake data when the SpringTrader app starts. So we're going to have a container for one of our jobs called generate schema, and it's going to run a script that we have already prepared to create a schema within our SQL Fire database. And then we are going to make sure that this generate schema job doesn't run until the database is ready, right? We can't seed a database with a connection or with a schema if it's not currently accepting connections, right? So our job itself also has an init container called wait for NanoDB server. So all we're doing is running kubectl wait for this particular pod to for its condition to be marked as ready. Once it's ready, that database is able to start receiving connections, and our job can start running our what it needs to do to generate the schema against that database. Any questions about jobs? Awesome. So with that, there's kind of a barrage of information there. So sorry about that, but we should be ready at this point to start containerizing our monolith. So we're going to start with lab 1. And we're going to use the Cloud9 environment and our local Kubernetes cluster that we provisioned in lab 2 to start iterating on this SpringTrader application hosted inside of Liatrio's GitHub account to fork that application, make some changes to it by adding some Kubernetes manifest files, and then deploying those changes to your local Kubernetes cluster and running it locally, and then testing to make sure the application is able to run successfully on your local cluster. So just like with Lab 0, I'm going to kind of get you started a little bit with some of the setup and then let you guys kind of go off at your own pace to make sure that you're able to start using your Cloud9 environment and running through these steps. So again, we've got kHignite.com, this link right here. I'm going to go ahead and paste this into general. So Lab 1. So if you guys want to go ahead and visit that link there, you can get started with this lab. And then just like last time, feel free to post some questions you might have or concerns inside of the support channel if you're running into any issues. Or depending on how quiet the Zoom call is, you can just go ahead and ask over Zoom and we'll be happy to help you out. But what we are going to do is get started with actually opening up our workspace and cloning this repository in your GitHub account. Hopefully you have a GitHub account. That's the same account that you used to initialize the SSH key that was generated in that workspace setup script. So we're going to start with cloning that or forking it over to your personal GitHub account, cloning it down, and then making some changes which are outlined in some of these other steps. All right, I'm going to let you guys loose. Go ahead and get started on that. Feel free to let us know if you have any questions or run into any problems.